this is the second half of today's colloquium. Frans Oort, we'll continue.
Okay, I will tell you now about Manny Mumford. Manny Mumford is the following. As I said, you take a torsion point, homogeneous variety, you take a gene subvariety, and you make a subvariety by beta plus b. Just translate b by beta. And of course, torsion points are dense in b, so beta filter points gives all the torsion points in this set, and it gives us dense subset of x. We just proved it. So beta plus b gives you dense subset of x. And just a little side remark, if you replace C by a field practically P, the original statement of the anti-motion conjecture is completely false. For the following reason, that over a finite field, every point on the beam variety is torsion. So any algebraic subvariety has a dense set of torsion points. So to characterize such nice special subvarieties over a finite field doesn't work at all. And actually, we have no idea how to do this over a finite field. So how to formulate a version of Mann-Mumford. And so here's the general conjecture. You take any Zariski closed subset, and you suppose that taking a closed subset, then it's affecting the torsion, and then Zariski closed gives you x back, then x is a finite union, translates by torsion points. So this is the version. This conjecture was proved by Renault in 1983. It's a beautiful proof, it's a staggering proof, and the first time I saw it, I was really amazed, because what he does, he takes such an invariant variety, then specializes to the number field, then reduces mod p, where the conjecture is false, and then studying reduction mod p squared to mod p, and doing differential computations, and then proves it. It's a staggering proof. Now there are much more shorter proofs. Okay. So there are many proofs now, and this seems to be one of those too. Okay, I want to introduce to you modular spaces. So you take a beam varieties, and you want to construct a big space where a point in the space corresponds one-to-one with an isomorphism class of a beam variety space G. And this is a fantastic theory. It's also already 19th century, considered both for curves for beam varieties, and Grothendieck and Mumford, using classical results and questions, made a complete picture. And this is really a rich theory, which you really can do mathematics. Of course, one of the basic things in mathematics is you have objects. Can you classify the objects by points in some set which you know very well? And modular spaces. Okay, here's a short description of the theory for elliptic curves. Elliptic curve is just over the complex numbers, complex one space divided by a lattice. That lattice you can give by a tau, like I did before. That at once tau. Tau classifies certain elliptic curves. Up to isomorphism, you can change by group delta. Please criticize me that you use delta, not gamma, but gamma was already in my talk. I mean, classically, this issue should call gamma this group. Let me call it delta. And then the modular space of elliptic curves over C is just the upper half plane, H1, mod out by delta. And there are lots of interesting questions here. An elliptic curve is said to have complex multiplication if it has more than if it has more anamorphism than just the Z. And let me explain the terminology. You see, the student with the thing complains. Suppose I have an anamorphism. Then on the tangent space, this is the tangent space, you have the differential of this, and this maps, and this of course equals multiplication by a complex number, and this complex number embeds lambda into lambda. So anamorphisms is the same as multiplying on the tangent space by a complex number in such a way that maps a lattice into a lattice. So that's the reason why we call this the theory of complex multiplication. And let me tell you something. Suppose you have a field L. This is called the CM field, and CM stands for complex multiplication. If this field is totally real, if this extension has degree 2 and is totally complex, and totally real means any embedding to the complex number automatically lands into the real numbers. So if L0 equals L0 beta, then beta is 0 of an irreducible polynomial, and if you draw the graph of this, right, this is for G5, this is the definition of a totally real number. You take the irreducible equation over Z, which has degree G, and where all the zeros are real, then this defines you a totally real number field. Okay, so that's the theory. Of CM fields, and it might happen. Yeah. Oh, sorry. I now go to B and right of dimension G, and you take the G upper half space of dimension G by G matrices, which is symmetric and close to definite. You divide out by the group delta, which now is the symplectic group, and that's the modular space of V and right. And you see how you do it. And V and right is just over the complex number, just C to the power G mod a lattice. That lattice is spanned by E, by G base vectors, just once, and G tolls. That tolls form a matrix, and you just have to follow your direction to see when such two are isomorphic and such are isomorphic correspond to each other on symmetric proof. On and real variety, which has complex multiplication by a field of 2G, which is a complex multiplication field, then we say that that point is a CM point or a special point. And I tell you the way you should look at these. Suppose you only know the complex numbers to start with, and you want to go down with your construction of your modular space to Q, or to the finite extension of Q. How do you do? Well, it turns out that the CM points are defined over a number field. So this large space over this large field has a lot of markings, and all these markings naturally live over a small field. And that's the way Shimura proved that all his Shimura varieties are defined over a number field. But just constructing the Shimura variety over the complex numbers, then marking all the CM points, that's a dense set of points, and these are defined over a number field, so the variety itself is defined over a number field. That's the system really goes. And the easy observation is that the CM points are classically dense. And the proof is exactly what I gave in the beginning, Namely, you must have points on your Ziegler space. So just imagine how you do it for genus 1. Then you must have imaginary quadratic points. So what I'm saying here, that imaginary quadratic points are dense in the complex plane. Well, that's completely obvious, right? So let me tell you something else. I constructed for an algebraic curve and being variety, and that gives you what we call the variety locus. So the variety locus is a set of being varieties which happen to be the Jacobian of the algebraic curve. And one of the main questions we have been considering is, you take on one hand the variety locus, on the other hand you take the CM points, and what is this intersection? And going back, what is the closure of the set of CM points? And that has been one of the main concerns of whatever we are doing. So I'll give you one example. I go very fast over it. Take any m, at least 2, it's a prime number, strange way to call prime number m, but that's the way we do it. And you take the equation y to the m is x times x minus 1 times x minus lambda. So when lambda is variable, this curve changes its shape. And of course, this m is 2, you know this is the Legendre normal form, but for arbitrary prime number m you can do this. Question, if you change lambda, does it happen sometimes that this curve has the mean variety which has complex multiplication? And how do you detect it? And the staggering fact is that if the m is 2, then you have elliptic curves, and then there are infinitely many CM points. But if you sit down and try to compute which lambda gives CM, you'll see that this is awfully hard. Because what is in between, on one hand, the complex torus comes from this imaginary quadratic field, and then the Weierstrass P function, it becomes the lambda, so to speak. But the Weierstrass P function is transcendental, so how would you ever compute from imaginary quadratic tau the corresponding lambda, and then conversely? Of course, there are power series for lambda in terms of tau, something like that, but that doesn't help you at all. So it's a hard question to write down lambdas which have CM. It's an obvious observation that there are infinitely many. And this is the source of all the researchers have been taking long. For some strange reason, there's no ramification at infinity in certain Rubies. So this is a fixed algebraic curve, and the lambda varies, but it doesn't change the algebraic curve at all. Then if m is 5 or 7, in this family, there are infinitely many CM fibers, but if m is a prime number, at least 11, there are finitely many. Now what's the explanation that for exponents 5 and 7, you have an infinite amount, and for m at least 11, you have a finite amount? And this was the puzzling question which I was faced long, long, long ago. And here comes the André conjecture. The special subvariety you see by taking an algebraic subvariety, which can be obtained as follows. You have the Ziegler half space. You have the Ziegler half space, and that gives you mod is delta, the moduli space. And I say the algebraic subvariety here is a special subvariety if there exists a group H, an algebraic group here, such that H, the orbit on the CM point, gives you this S. Now this looks very puzzling, but let me explain you. This group, this space AG, looks like a group object. And what I'm doing, I'm only asking what are the subgroups. let's go back to Mani-Mumford. Mani-Mumford, you have an A, and you're looking for special subvarieties. And special subvarieties are Argean subvarieties translated over torsion points. Now, what I'm doing here is exactly the same. Namely, I take the H, which is the equivalent of the Argean subvariety. I take the torsion point tau, which is the equivalent of the torsion point there, and then I translate, instead of adding in that stage, I translate, and such a translate, I call it special subvariety. And so this, warning, you really have to suppose that S is an algebraic subvariety, and by dense, I just tell you that and by dense I really want that's risky dense. Okay, now the conjecture which Yves André and I did independently, you take V, which is the moduli space for being varieties, mind over the complex numbers. And you take any set of torsion points. So, to take your intuition, take one of the families we had before. Y to the n is x times x minus 1 times x minus lambda. And take all values of lambda for which this is the CN point. Now that's an example of gamma. Question, can I tell you what the closure of this is? And the conjecture says the following. The conjecture says that the heuristic closure is a finite union of special subvarieties, or if you take an algebraic variety with a dense set of CM points, then it is a special subvariety. So that's the way this conjecture works. Let me tell you that there is a close analogy between Mani-Mumford and Frans Oort, and actually Yves André and I were guided by that analogy. And I've said already many times, beta plus B, where beta is a torsion point and B is a leading subvariety, that is the candidate for something where the torsion point is dense. And the special subvarieties are something where the CM points are dense. The torsion points in Mani-Mumford and the special points on the word CM points are the analog. And so if you just copy the Mani-Mumford conjecture, you come to this conjecture. Unfortunately, or happily, the proofs of the Mani-Mumford conjecture, if you transport these on the Oort case, you don't get anything. Of course, we tried that many, many times. Okay, so that's what I'm saying. Just translate this terminology to this. Let me give you one application of on the Oort. The question is, does there exist in the B variety, which if divided out by a finite subgroup scheme, becomes a Jacobian? And of course, if it is already a Jacobian, that's no point. But do there exist to be varieties which, up to isogeny, do not belong to Jacobian? And I write, so x is the modular point of A, and then this I call the set of all points which isogenously be right. This is the set of modular points over B, where B is isogenously to A, or B is A mod satisfying. This I want to intersect with the Redi locus, and I want to know what it is. And can I find an x such that this is empty. And Qingli and I were working on that many times. Well, if the G is at most 3, that's certainly not the case because then the modular spaces are the same. But if G is at least 4, then this dimension 3G minus 3. It's less, strictly less than a half times G plus 1. So then the situation really makes sense. For the complex numbers, this is obvious. Because the Hacker translates of these Torelli locus, that's a countable union of lower dimensional subvarieties, and over an uncountable field, you certainly do have a point outside of the countable union. So, over the complex numbers, the answer is yes. Look, and not necessary. Okay, over another field, over Q bar, Qingli and I have proved recently that for any G, at least 4, there exists a linear variety over Q bar, which is not exogenous to a Jacobian. And the way we do it, but I don't want to give all the details, we take CM fields, and for every CM field, we construct an linear variety, and we intersect each Hacker orbit with TG. Now, then you get CM points in TG, and these CM points in TG, if you assume André Oort, its closure is the finite union of special subvarieties. So you get a finite number of special subvarieties. And some of these are zero-dimensional, okay, that's a finite number. And then the other one, you want to know whether there is a Shimura subvariety or a special subvariety in Torelli locus. And then Qingli found a beautiful idea of not considering CM points, but slightly more restricted kind, what we call wild CM points. Then proved that the wild CM points, if they are on the Shimura subvariety, the special subvariety, then that's a Hilbert variety. And then de Jong and Zhang proved that those are not contained in the Torelli locus. So all of a sudden we see the steps. You take this set of points, loose set of points, you have no idea how they look like. You take this risky closure, use André Oort to produce from that the fact that it is a finite union of closed subvarieties. These closed subvarieties you know very well, they're special subvarieties. And then you see whether they can be contained in the Torelli locus. Now, we had to use André Oort, but André Oort was at that moment only proved under assumption of the general Riemann hypothesis. But Jacob Zimmermann, here in my talk in Princeton, all of a sudden jumped to that idea and proved that in this special case, you can avoid the general Riemann hypothesis. So the theorem also bears its name. So this is a beautiful example, and I hope you see the string of thoughts. You first have these CM points, it's a strange set of points, but it's a risky closure. You know exactly what it should be. And these subvarieties, you know a lot, so that's okay. Okay, then I come to my last, I have 5 more minutes, you need that? Okay. The Hacker orbit conjecture says the following. I now move to characteristic P. And the characteristic P, I take a point, X, in the modular space. This is the modular space over the characteristic P field. And we look to all being varieties exogenous to the original one. And over the complex numbers, any Hacker orbit is dense. And that's exactly what I did before. Namely, a Hacker orbit is just a symplectic group over the wheels operating on the point. So the Hacker orbit is the symplectic group of Q. So if you know the deep fact that Q is it's classically dense in the real numbers, then this group is classically dense in the symplectic group of real numbers, and symplectical real number just gives us an orbit the whole modular space. So to prove the Hecke orbit conjecture over the complex numbers is obvious, and any Hecke orbit is dense, and that's easy. It's classically dense and hence it's heuristic dense. Question, how does this work in characteristic P? So we change our point of view, we fix a prime number, we take a modular point of characteristic P, and we ask what's the risky closure. And there's one observation. If you take what we call a supersingular elliptic curve, that's an elliptic curve with no points of order P, then that curve has a finite Hecke orbit. So in that case, this is a finite set, the risky closure is a finite set, and it's not the whole modular space. So all of a sudden you see it, characteristic zero results don't prove anything. The characteristic zero result, it's a dense set of points, and if we lose no P, all of a sudden, as flowers in the vase, they come to just a finite set of points. So that's what we do with elliptic curves. For the ordinary, for the elliptic curves, you do have a point of order P. Clearly, the Hecke orbit is dense, this for G equal 1, but for elliptic curves, no points of order P, it's not dense. And just a finite set of points. Question, how can you formulate the Hecke orbit? Problem is, what can you prove? And both Ching-Li and I were thinking that about the same time, beginning of the 90s. And so let's say the mean right is ordinary, you have to have the maximum number of points of order P. And then for the mean variety, you construct a Newton polygon to distinguish the ordinary and the non-ordinary case. In higher dimension, there's a more subtle invariant. And the more subtle invariant is what we call the Newton polygon. And the Newton polygon is basically the classical Newton polygon of the Frobenius. The Frobenius satisfies the minimum equation. The minimum equation has coefficients. The coefficients have p-adic values, and that gives you a polygon. That's the Newton polygon. And you can easily see that the Hecke orbit is contained in a closed set of all points having the same Newton polygon. For the simple reason that if you apply a Zarginus, the Newton polygon doesn't change. So this poor Hecke orbit tries to escape, but it has to remain in this closed set. And then at the same time, Ching-Li and I had, one of us two had a beautiful deep theorem, and the other has a vague thought. And the beautiful theorem by Ching-Li, proved in the Jonas, published in the Jonas, is that for every P, for every G, and for every ordinary point, the Hecke orbit is dense. Now, if you think you can do this by just doing it correctly for zero, where lose mod P, that doesn't work. And this theorem is really extremely involved, and I was completely flabbergasted when I saw it for the first time. I was visiting Harvard, and I gave a talk for the Harvard algebraic geometry seminar. They were quite impressed by this beautiful proof. So this is the theorem by Ching-Li, and at the same time, I had the conjecture that this Hecke orbit, the risky closure, is W(psi). And since then we have been working on this, and now this has been proved. Ching-Li and I have struggled. We have a proof which doesn't work. To our dismay, there is another proof which involves Hilbert's modular varieties, and then we asked the help by Checker for you, who was very kind to help us in a beautiful theorem on the Hecke orbit problem for Hilbert's modular varieties, and all these combine into now the proof of this conjecture. I have told you three conjectures. I didn't say anything about the proofs. And the question is, are we finished? Well, there's a mathematical theory that as soon as you prove anything, more problems come up than you solve. And that's the case also in our case. So I mentioned you a few open problems. One problem is to formulate on the Oort conjecture a positive characteristic. And Ching-Li and I have worked on that several times, and many times you know, aha, now we have an idea, and then we worked it out, and then completely failed. So we have no idea what a good candidate is of this under-Earth conjecture, but I would emphasize that that really is something which you really want to characterize special subrights in practice. Okay, so many times we were on the wrong track, and it seems that really fundamentally new insight is necessary. This new insight, I will come to that. I mentioned this problem, the Honda-Tate theory, and proving it using only methods of algebraic geometry, and I think we have solved this, but I don't want to claim that because we haven't written out complete proof. The Hacker-Orbit problem is now proved for what we call the zero case, it is for the modular plane being varieties, but we should also like to do this for arbitrary Shimura varieties. And it seems that the interplay between Hacker actions and deformation theory seems necessary. It's a better proof, which Chingy and I are trying to find, would allow us to also approach the Shimura variety case, but we're completely stuck at the point. I've proved to this conjecture for over complex numbers, the answer is yes. Over Q bar, the answer is yes, and not the word. But over F3 bar, we have no idea. So the question is, if I give you any G, at least 4, is it true that there exists in being variety over F3 bar, not as often as you call? And mind, the proof I had here, what was the proof here? I take all Hacker translates of the Torelli locus, that's a countable union of lower dimensional subvarieties. So that might of course happen that over F3 bar, the countable union of Hacker translate of a lower dimensional subvariety might not eat everything. So we have no idea. And it seems that really that we lack completely insight into some fundamental structure behind this problem. I think all of you, as we're sitting here, are very curious. Asking questions tries the structure behind the problem. Urimani in a beautiful interview once said, good proofs are proofs that make us wiser. In the beginning of my talk, I emphasized problems and the Feynman way of looking at problems, but Urimani disapproves of that in a sense, because he says, I see the process of mathematical creation as a kind of recognizing pre-existing pattern. So it's not the examples which are important, but it is the pre-existing pattern. Okay, thank you very much.
Thank you for this wonderful talk. Are there questions or comments?
Yes.
So, in the statement of the F-orbit conjecture, do we have a refined statement? For instance, in the case of Hilbert module varieties, we take the ordinary C and varieties, and we consider C and variety as attribute to this one.
Yes.
And then it's still dense. I guess it's still dense.
Oh, sure. Yeah.
Yeah. So
that's
we
what
don't
you
need
proved that the Hacker-Orbit problem on the Hilbert model varieties.
Yeah, so we don't, my point is that we don't need all points to be X subject.
No.
So my question is, so we have a refined statement?
Refined statement?
Refined statement, so for instance, take a point X, we can hit smaller point to be X.
Yes.
And we still get this.
Let me see whether I understand the problem. Which variety are you working with? The Hilbert model variety?
So for the Hilbert model varieties, we take